Hello, thank you for choosing my presentation. My name is Camden Pankratz. I am a physics student at University of Northern Colorado in Greeley, Colorado, and this will be a comparing a math first versus a physics first pedagogical approach to general relativity at an undergraduate level. First, I would like to talk about how I'm going to go about this presentation. I'm going to have an introduction first, then tackle the math first approach, and then the physics first approach. And then I'll have a little bit of discussion on which I prefer and the benefits of either, and then finally resources that I pulled from. So what is general relativity? It's been in the news, it's been in pop culture with movies like Interstellar. Recently, LIGO's facilities detection of gravitational waves have been all over the news. There's a lot of GPS satellites need to account for it, our cell phones need to account for it. So what is it? Why is it such a big deal? So let's start at the beginning. General relativity was first published by Albert Einstein in 1915. It is a geometric theory and is the current gravitational model used in modern physics. It combined the Newtonian physics, the physics that used an apple to fall, and how Newton observed it, but he also combined it with his special relativity and the theory that the speed of light is actually the all-encompassing speed limit of the universe. And this actually focused on how things actually work and how gravity can actually slow down time. This is a very complicated thing, and Einstein was able to think it out. So we're going to take a look at how we can approach to learn this. So what is relativity in modern physics? It's one of the four fundamental forces in modern physics, along with the strong force, the weak force, and the electromagnetic force. Unlike some of these forces, though, it's not limited by distance. It doesn't have a repulsive force, which means it's always positive. It is always going to be pulling in, so it's unscreened. But by far it is the weakest force that dominates over cosmic scales, though, because it's not affected by distance. This force is what holds our galaxies together, what holds our planet going around the sun. It dominates everything in a cosmic scale, but we don't necessarily feel it in our everyday lives, other than keeping our feet on the ground. So what can we do to analyze this? Now, Einstein thought about this for a very long time. What can we do to understand? I don't understand. What is this doing? How are we approaching this? He came at it from geometry, and it's actually curved four-dimensional space-time. Mass itself has an energy that gravity acts upon. So as you look at it, if you look at the picture on the right here, he actually proposed that if we were looking at a flat plane, that gravity, if being a point right here, a massive point, a particle would actually sit and curve around it. In three-dimensional, the Schwarzschild came up with the metric after Einstein published that looks like this, that actually projects onto a flat surface this exact thing. And watch this particle go and dip down closer, and then it comes back out. What it's inducing is that free mass moves in straight lines in curved space. Now that is a very interesting thing to get your mind around. So what that means, think about it. If you are looking at lines of longitude on Earth, if you are heading north parallel to someone, you can actually go straight and you feel like you are parallel. But if you guys would to actually meet at the North Pole, you would run into each other. And you're no longer parallel because you can't run into each other when you're parallel. So it doesn't exactly, it's one of those things that Einstein would think about, understanding that not everything appears to be parallel. And that is where he came up with the idea that mass does move freely in straight lines, but yet the space is actually curved. So it's going on the surface of the Earth. It's a curved surface, but it appears to us like we're going straight. Now, how did Einstein describe this? It is a very difficult thing to describe. he decided that he would use 4 dimensions in math. It is something with math we can go into the abstract world that our 3-dimension can't actually illustrate. So, as you can see, he has a 4-dimensional space, and where he used his dimensions as 0, 1, 2, and 3. Now, his equation right down here, which is the Einstein equation, is solved by a metric, which is this g of sub alpha sub beta of x. So what is a metric? A metric is a 4-dimensional differential manifold, and the metric is given as a covariant, which is a second-order symmetrical tensor on a 4-dimensional manifold, which is described by a 4x4 matrix. More generally, it can be thought of as a generalization of the cross product in ordinary Euclidean space. It's not an exact analogy, but it's pretty close. So this metric we would use determines the squared distance, which is the ds squared here, if you look. It determines the squared distance in 4-dimensional spacetime between 2 points that are separated by infinitesimally small coordinate intervals. So what we're doing here is actually we'll be integrating this over dx superscript alpha and dx superscript beta. Now what that is it's a double sum over alpha and beta from 0 to 3, those 4 dimensions that are implied. The integration of ds specified from this expression gives us the distance of a particle in an Einstein field and its travel across that, and the distance that it would actually travel going across that 4-dimensional field, thus solving the Einstein field equation down here. Now below, the Einstein field equation here, sorry, I'm going to step back just a little bit. The Einstein field equation here is no simple equation either. It is one of those that it is comprised of 10 nonlinear partial differential equations to give the metric of g sub alpha sub beta. So it's a very difficult thing. At this point, we've already talked about you need a background in calculus, differential equations, and linear algebra, and then you also need the experience with these subject fields to be able to manipulate them to the point that you need them. So we're looking at, if you look at an undergraduate course load to address this very well, you would probably need to maybe address a topology course to help out with that advanced problem solving. Now a famous solution down here, which if you saw earlier in the slide before this, of the Schwarzschild metric, which is on the bottom, which is in that curved 4-dimensional space-time, is he had actually proposed a solution right a year after Einstein published that was in the traditional spherical coordinates that we are familiar with. And he came up with this solution here, where m, the big M here, is the mass of a black hole or planet or star, the massive object that is affecting the path of this particle in this field. And r is going to be the radius of that. Time is obviously t, and then along with that you have theta where the angle is, and phi where the angle opposing to that on a different axis. So everything else is pretty standard. G is the gravitational constant and c is the speed of light. So this equation here defines the path, that ds squared, that the path that particle would travel in the Einstein field. So this is very difficult stuff. It is not exactly stuff that most undergrads would see in a lot of physics in physics curriculum, or even a lot of like secondary math or secondary education math or applied math curriculum. So it is a very difficult thing, and it's not often accessed to the undergraduate level because of the level of the prerequisites that you're actually looking at. As I said just a little bit ago, prerequisite skills are needed in this. Any approach, it will take time to develop the necessary skills. The biggest problem with relativity is we need more time, not to be a little bit of a pun there, but we do need more time. So, if I were to approach this from a math first standpoint, so very common curriculum from a math, traditionally you would introduce the necessary math skills to address these. So, in this case, it would be calculus, linear algebra, and differential equations. You need to motivate the equations. So, what we're looking at is work with differential geometry and then use the equation, the Einstein equation, as an example of what we're looking at. Then we would solve the equation in a particular instance. So I'm going to put a particle in this field right here. What behavior it's going to do. Then you would apply those solutions to make predictions with observational data. So then you're looking at experiment data. Now you're looking at that, and then looking at computational expectations, so you're being able to predict how that particle would behave up in space. So let's review that again. We would first learn the skills, then motivate the equations and explain them. So we learn the skills, look at the equations, and learn what the equations are actually saying from the skills that we just learned in the math, and then we would start looking at examples of that equation, and then start being able to take predictions of, okay, we see this this up here in space in this telescope, we know it's in this position, this is how it's going to behave. Let's apply this to something that we're more familiar with at an undergraduate level. Let's look at electromagnetism. So in this one, we're going to first introduce vector calculus, and now we're going to start looking at the Maxwell field equations once we've learned that vector calculus, and use it as an example of what vector calculus can be applied for. Then we're going to look at boundary problems, fields of point particles, radiation fields, applying what we've learned to that as an example. And then applying to charged particle motion, circuits, antennas, being able to predict how antennas will behave, how everything from particle motion in a uniform electric field is going to behave, and then how circuits, maybe looking at how resistivity might behave. That is a math first. If you notice, we'll look at the vector calculus first, and then use that to use the Maxwell equations as an example in vector calculus. Then applying that Maxwell equation after that. So what would this look like in relativity? All right, so now we're looking at what we're actually here for. So let's look at the first thing we would do in a math first approach. We would introduce differential geometry. Now that is going to take linear algebra, differential equations, and calculus to get to it. So that in the combination of all of those is going to be what differential geometry. That is the definition of differential geometry. Looking at geodesics and how things apply to curved space, curved surfaces like that. You look at how, like, okay, let's look at how can I find the surface area of a golf ball with all the dimples acquired in there. That is something that you would maybe tackle in differential geometry. Then we're going to motivate the Einstein equations and geodesic equations as examples of that differential geometry. Applying those equations to spherical symmetry, cosmological models. Now we're going to look at gravitational waves, relativistic stars, how even there's been how the moon would actually even bend light, or other our sun actually, not necessarily the moon, but our sun, how that would bend light of stars behind it. If you look at the everyday applications that are used, so how can we use this in GPS systems and studying neutron stars, the Big Bang, formation of black holes, all the cool stuff, but you don't get to that until the fourth step. But you have a great understanding of the differential geometry once you get to that step. So let's look at a math first approach to these two pictures. One being how a star would affect a particle in its curved field, and then the other one being a black hole or a massive star where there is a singularity, if you see all the way at the bottom there. So what this is, if you actually look, a geodesic is actually a straight line around there. Think of it as the great circle going around the globe. We're following this particle right here. This particle never turns, like if you were to turn a car. But the gravity of this star actually, you trace the field here, would go off there. And then this is a deflection. I'm not going to talk about that, but what I want you to see is this particle in a field kind of equation here. So first, I would look at math and the differential geometry of what I'm looking at first, and then use these as an example that I would solve for in applying that math. That would be a math first approach of this field for you. Then you're looking at how would I apply this. So I want to predict what a particle here is going to do. And then I could actually predict it out here after I've learned all the other stuff for you. So that is how you would approach this kind of model from a math first approach. You would learn the necessary tools first and then apply it to the situation that you're using it for. So what is beneficial about this approach? It is a very logical approach. You learn what you need to know to approach the problem at hand. You're gaining tools in your mind. You're training your mind to do that. It promotes a greater understanding of the theory behind it, so you have more of an ability to manipulate the equation and to understand exactly what each variable is going to tell you, and if you do one thing, how is it going to affect another constraint in the equations. And it satisfies the rigorous purist student that wants that theory behind it, that wants to know how everything intertwines with it. It is a little bit more rigorous. Now, why is this not beneficial? It needs more time. You do have to establish the prerequisites to, I'm going to once again state them. It's calculus 3 that you have to get through. So multivariable calculus, you're looking at linear algebra, and then differential equations. And to effectively, some would say that you need a topology course to gain the skills of problem solving and how to apply things. So it would be limited primarily to senior level undergraduate students, and then the graduate level students at that point with those prerequisites. But it is very doable for the math first approach, and it is a very viable method. You do get the better theory. You get a lot of things, and that pure student is going to be very happy with that. But it's not the only way. So let's take a look at the physics first approach now. So the physics first approach is traditionally exhibiting the simplest physical important examples without derivations. What this means is analyzing the behavior first. Then you derive predictions from the example. So, hey, what is this behavior doing? And what will it do if I do this to it? Then you're applying those examples to realistic situations. So, okay, so we learned this and this about just watching it. So if I were to need something to do something, what could I do to it to make it do this behavior? Then you're going to use that, okay, so hey, this is what it's doing. Now we're going to look at the equations. This is actually what's happening. You've already learned the behavior of it. You've learned what each one, how the effect is on each one of them. Now we're going to learn the math. Now we're going to go ahead and do the rigorous calculations that we can do. Let's go back to our very familiar example that we were using. So let's go back to electromagnetism. Let's revisit this. Maxwell's field equations in vector calculus are not really mentioned in most general physics textbooks. You don't necessarily get them. You can look at here at UNC, it's Physics 240 and 241. They don't actually mention them. They mention them, but they never explicitly state them or actually introduce them. What they do is they introduce the simplest example of the Einstein field equations, or not the Einstein, sorry, Maxwell. We're not there yet. Of the Maxwell equations, and like particle in a field, how does this behave? I remember from my physics course that they would say, okay, so if you put this particle in a magnetic field, and what would it do? And we had to predict that. So we're looking at, okay, let's look at how this behaves first. Now let's use that behavior to predict something. Then we're going to get then we're going to start looking at, okay, how is this really affected? What's the mathematical translation of what we just did? So let's apply this approach to something like general relativity. First step, we would exhibit a simple space-time geometries first, without derivations. So if you think back to that particle and field pictures I had right after in the math section, we would look at that behavior first. We don't have any of the equations. We just want to analyze, hey, what's going on? Then we would derive predictions from the observation. Okay, so we're going to go from the top picture to the bottom picture, and I'll show you this here in the next slide. We're going to look at, okay, so if I have this situation, what's it actually going to do? Now I'm going to apply these predictions to realistic astrophysical situations and compare them with experimental and observational data. So how can I look? Okay, we observed this phenomenon. This was an experiment done. They observed this phenomenon where if we blocked out the sun, we can actually look at the stars behind it, and they actually are different positions depending on what side of the sun they are. This is actually a description, a real-life experiment that demonstrated how general relativity bends light around it. So then we would use that example to motivate the Maxwell or the Einstein equations. I don't know why I'm switching those. The Einstein equations, and solve them for the example that we used earlier in those fields. So let's take a look at those fields and analyze how we would approach those. So here's our example we used earlier. Here, so we can actually analyze, we can say, okay, so we have this field here. This particle is going to go from here and go around there and come back out over here. So that's the path it's going to follow, and we can actually observe that path. So what we're going to do, okay, so we have this whole equation, or this whole example here. What does that mean if I have a singularity or a black hole there? What is it going to do? So now we're going to predict what is going on here. So we have this particle. So we know it's going to have a very similar path that it's going to be up here. So we're going to predict that. But what if it gets too close? How close is too close? That's that red line that we'd have to do a little bit of calculations, but we use our predictions here, and then we test those predictions, and then we find that the the no-go zone here is that red area right there. So what are we doing here? We are using experimental data to determine something. Now we learn that this can be actually described by the Einstein equations. We can actually apply these principles that we just learned to the real world. How can we calculate general relativity corrections for satellites so make sure our cell phones are on time? How can we do this so that we can track how planetary orbits are going to be there, and if we want to go to Mars? These are the applications that these physicists are using, but they're using these to go ahead and approach how these are examples that they're approaching general relativity with. So that's how I would approach these pictures from a physics first standpoint. So what is beneficial about the physics first standpoint? We're going to focus on applications of it, so real-world applications that get an experiment down to a lower level. It uses mechanics and conservation laws, using intuition, so it's going to be easier to learn using stuff that you've already established in your student's brain and psyche. There's fewer prerequisites to look at this because it's not as math heavy, so it brings students closer to research applications, looking at GPS offsetting, and also astronomical observation stuff that we can actually offset and then measure distance of stars. Now, why isn't this beneficial? It's not necessarily the most logical progression as far as like to teach someone. It's not a traditional teaching method. Might annoy the theory purist students, like the math first would actually would help more. So it's not going to be as rigorous as they might like, and it wouldn't benefit the student with the time that wants to study it, that has the time to do all the more rigorous course of study. So what does this say about math first and physics first in my book? I personally, I am a very observation first and then describe it later person. I prefer the physics first approach, but I also thoroughly understand why the math first approach would be more effective, because you learn it at a more core theory level. That doesn't always happen until you work more and more with it in the physics realm of things, if you weren't to address it from there. So it really depends on if the student or any program is going to focus more on a physics first application, or observation data and experimental standpoint, or if they want to do a theory application. It really comes down to what the institution or the individual student wants to achieve out of it. What do they want out of it? So it's one of those things that is a very difficult standpoint, or very difficult subject matter, and it really comes down to a personalized approach to it. It's some ways aren't the best for the others, so it comes down to, you need to be able to weigh the benefits and the cost. That being said, there's some great textbooks out there. Let me show some of them to you that I actually looked at a little bit. I didn't have enough time to go and read through them all, but the reviews I read are fantastic on them. So here, let me show. Here are those books that I was talking about. First one up is the book that almost every professor teaching right now general relativity probably learned from, which is Gravitation by Meisner, Thorne, and Wheeler. It is a large book, but it is a math first book for you. So they do teach you the math and then apply it to the gravity equations from Einstein. Now you're looking at something that's been written a little bit more recent. It's called A First Course in Relativity by Bernhard F. Schutz of the Max Planck Institute of Gravitational Physics in Germany. They are a very similar approach to it, but a little bit less of a large book. This one's probably about 400 or 500 pages instead of 1,200 that Gravitation has. Both very good texts and very very comprehensive text as far as that goes. Now, looking at a physics first approach, I would suggest taking a look at, if you're curious, of Gravity by James Hartle of UC Santa Barbara. He was one of the ones, and he actually does claim to have taught, and not just him, but other professors there with other denominations in physics, have successfully taught undergraduates from his book on 40 different courses so far. Also from UC Santa Barbara, there's a really good one, a little bit more rigorous, a little bit more in depth, is going to be Einstein's Gravity in a Nutshell by Anthony Z. This one is personally my favorite. It does explain things extremely well. Gravity by Hartle does a very good job too, but Einstein's Gravity in a Nutshell does have the analogies that make it a lot more of a real world application to it, and I do prefer it that way, and it reads a little bit less textbooky in my opinion. So all of the four of these are going to be very good resources if you guys are curious on what approach you want to do, if you want to check them out. I found them at my university library, all four of them. I'm sure that almost every major university would have them there. If not, they can request them. So I would like to thank you guys for watching this presentation. These are some of the sources I used. I used an article by James Hartle, which was addressing how to teach it to the undergraduate in the physics curriculum. Then also Christensen and Moore's Teaching Relativity to Undergraduates from Physics Today. It was a great article if you guys want to check them out. I also had consulted Dr. Dean Allison here at UNC, is the math department chair, because he has done some research in general relativity, and he was a great resource to bounce some ideas off of, like curriculum ideas off of. Once again, thank you for watching my presentation, and let me know if you guys have any questions. Thank you.